So it is a pleasure to introduce Eugene Speer in this seminar. I met Eugene many years ago when I was a postdoc in Rutgers with Joel Lebowitz and Shelly Goldstein, that are also co-authors of the papers that Eugene will present here. It was a really very nice time for me when I was there and discussing with Eugene, Goldstein, Eisenman, also all the postdoc, Anna De Masi, and De Suti, Spon, many people I met at that time. I have liked to work with Gene directly in a couple of papers, and also I was very influenced by a paper he wrote with Derrida, Lebowitz, and Janowski about the two-class exclusion process. And now Gene today will give us talks about these one-dimensional facilitated exclusion processes. So Gene, you can start when you want.
All right. Thank you. Thank you very much, Pablo, for the invitation. It's very pleasant to be here. As Pablo said, this is joint work with Shelly and Joel, and also Arvind Ayyer, who used to be a PhD student of Joel's at Rutgers and is now in India. So we're talking about facilitated exclusion processes. So these are like the usual exclusion processes. Particles sit on lattice sites in a lattice, at most one particle per site. I write the state space as X, that's just 0, 1, a hole or a particle at each point, and I use eta for a configuration. Now, particles, as usual in an exclusion process, can jump to a randomly chosen neighboring site, but to do so, they need to have at least one occupied neighboring site, which obviously they can't jump on. That's the facilitated part. I'll be talking about actually 3 pieces of work, and it involves 2 types of evolution. One is the usual continuous time evolution, so that's quite familiar. Each particle has also an alarm clock, which rings at rate 1, say, and when the clock rings, the particle attempts to make a jump, if possible. More interesting phenomena for us happen in discrete time. So in a discrete time system, all particles try to jump at the same time, which we take to be a positive integer time, and you can then have conflicts. 2 particles can attempt to land on the same site, and then one is chosen at random to succeed. All right, what do I want to discuss? I will discuss very briefly what's going on in d greater than 1. We have no results. I think these are hard problems in d greater than 1. One of the models is the totally asymmetric model, F-TASIP, facilitated TASIP, in discrete time. This is these 2 papers with Shelly and Joel. And so this particle can jump to its right because it has an occupied neighbor. It's totally asymmetric, so all jumps take place to the right. This particle can also jump. This guy can't jump because he has no neighbor to facilitate him. This guy can't jump because the space to the right is occupied. The same model, more or less, in part with the partial asymmetric thing, and this is done in continuous time. So in this case, a particle jumps to the right at rate p, and a particle jumps to the left at rate 1 minus p. Because it's continuous time, you can't have any collisions in this case. No 2 jumps take place at the same time. And finally, I'll go back to a discrete time model. This is the symmetric model, the F symmetric simple exclusion process. And in this case, particles jump either at discrete time, so at integer time, any particle which has a neighbor tries to jump. This guy jumps to his left because he's got a right-hand neighbor. This guy jumps to his right because he has a left-hand neighbor. This guy can't jump at all. And again, we can have collisions where 2 try to jump on the same place, and then only one of them succeeds, one of them chosen at random with equal probabilities. We'll be talking about 2 fundamental questions. First of all, what are the extremal translation invariant states? You'll see ETIS written frequently. Extremal translation invariant stationary states for these processes. Just a brief comment, we have conservation of mass, of course, so that each state, if it's extremal, each state will have a definite density, which means for d equal 1 that almost surely, almost every eta satisfies an equation that the average number of particles in eta is equal to this density rho. And then there will be at least one state for each such state for each density. So that's one question. The second question is, as you'll see, it's interesting for us. So we start the system with an initially completely random distribution, that is a Bernoulli distribution at some density, and we ask what happens. That's interesting to us, at least in some cases, which we'll come to. So keep in mind those two basic questions. And immediate observation, if rho is less than or equal to 1/2, so if the system is less than half full, then the system can reach a frozen state in which no particle has an occupied neighboring site. So in the extreme case, when the density is 1/2, you just put a particle on every other site. Nothing can happen because no particle has a neighbor. On the other hand, if rho is bigger than 1/2, this is impossible. The activity will continue for all time because at least one particle always has a neighbor. Now let me talk about D bigger than 1, 2, and 3-dimensional systems, where we only look at symmetric jumping. Here, I haven't done any work, but other people have done numerical work, and the numerical simulation suggests there's a critical density such that if you're below the critical density, everything has to freeze. There's no continued activity. But if you're above the critical density, there are active states. That is, there are these extremal translation variant states. Well, they don't prove that, but that's the idea, where there's continuous activity. The previous remark shows that this critical density has to be less than or equal to 1/2, because if you're bigger than 1/2, then you certainly have continuous activity. Unfortunately for us, we will always have a critical density of 1/2, which makes things a little less interesting. However, simulations by these people suggest that even in 2 dimensions, we have a critical density which is much, much below 1/2, only near a quarter. Well, that says that in this whole range between densities 1/4 and 1/2, you have these frozen states around that could trap the system, but the system can avoid being trapped for all time. It can simply go on with active motion. So this suggests 2 open problems. I'm a little embarrassed to state the first one. This first problem should be very easy. Prove that that the critical density is positive. So that's, you laugh at me, you say, of course. That says if you have a very small density, then the system has to freeze. There couldn't be an active system with density 10 to the minus 23rd. I agree, but we don't have a proof of it. Then prove that something like this happens, that in fact, there is a critical density which is strictly less than 1/2. And I think that's a hard problem. I don't know how to do that at all. Okay. All right, so that's all I have to say for D greater than 1. The first model that I actually want to talk about that we worked on is, again, this facilitated, totally asymmetric process. I've drawn the picture same as before, and again, all particles attempt to jump at the same time. Now, to see what's going on here, it helps to think about blocks of consecutive particles. So here's a block of size 2, here's a block of size 1, here's a block of size 3, here's a block of size 0, right? Because we have no particles in between these 2 empty holes. Now, blocks of size 0, two consecutive holes cannot form spontaneously. If you see this, it's been there forever, because there's no way that can happen. If you had a particle couldn't jump out from here, because this would have had to be full already before a particle could jump out. If you have a block of size 2 or more, it cannot grow. So here's a block of size 3. Of course, it dumps a particle, but it will also it might not dump a particle, but it may or may not pick up a particle. So it can't grow, it can only get smaller. And there's a tendency for large and small blocks to move toward the mean. So for example, if you have a block of size 2 here and a block of size 0 adjacent, this jump will take place. You'll end up with 2 blocks of size 1. Or if you have a 3 and a 1, the jump takes place and you end up with 2 blocks of size 2. So if you think that through, you find out that in no steady state can you possibly have blocks of size 0 and of size 2 or more, because they would annihilate like this, or blocks of size 0 or 1, small blocks with blocks of size 3 or more, because they would annihilate like this. All right, that means there are three possible kinds of states. There's low density states. These are blocks of size 0 or 1. There's no large blocks. That corresponds to a density less than 1/2, or in the terminology I used before, these are frozen configurations. Nothing can happen. That's the only possible situation for an ETIS state at low density. Intermediate density is density between 1/2 and 2/3. Now you don't have blocks of size 0. That means you don't have any adjacent holes, and you don't have any blocks of size 3 or more. So here's a picture of one. You have blocks of size 2 or size 1, that's all. Now, if you just look at this for a minute, you realize that in this situation, this whole configuration is going to translate with velocity 2 to the right. So this particle is going to jump there, but if you look at the big picture, that corresponds to this block of 2 having jumped 2 units to the right. This block of size 1 will stay there, but this thing ahead of it will become a block of size 1. So that's what goes on there. High density is rho greater than 2/3. Now all the blocks are size at least 2. And now these translations move with rate 1 to the left by the same kind of simple analysis. So what's important now to realize is that if you take any kind of these classes of configurations and put a translation invariant state on it, then it's stationary, because the evolution corresponds just to translation, no evolution here, translation to the right here, translation to the left here. And if you've got a state supported on a state which is translation invariant, then it will be stationary automatically. So the first question has just been solved. We know now what all the stationary states are for this model. This just fills in what happens at rho equal 1/2. Exactly, that's between the low and the intermediate region. There's a unique state which sits on these two configurations, the alternation of 1 and 0. And at rho equal 2/3, there's again a unique state. It gives equal probability configurations for density 2/3, the simplest ones, which have 0s and 2 1s. You get that by just looking at the restrictions. On the previous slide, these are the states which satisfy all the restrictions, both the restrictions for, say, both the restrictions for the high and the intermediate density regimes. All right. So now what do I want to do? We know the TI states. The question which is left is start with a Bernoulli measure. So I'm going to analyze the behavior separately for each region. Let A to T denote the configuration at time t, and what we can do is determine the actual limit of that configuration. It really has a limit, at least after you use a trick. I'll tell you about the trick, but once you've done the trick, you find a limiting configuration. So you start with any A to 0, and you get a limiting configuration A to infinity. And now we assume that the initial one is distributed according to this Bernoulli measure, and we try to find the density of the distribution of the limiting configuration. The key tool for doing this is height profiles. I'm about to explain that better, but basically we take a state and we assign to it a certain height function like this. How do we do that? With A to T, we associate a height profile, which I'll call HT. So that's something like what we saw on the previous page, something like that. The main point is that this formula, I should have written something a little clearer, but it's clearer down here. When you have a 1 in your state, the height profile goes down. When you have a 0 in the configuration, a hole, the height profile goes up. So that traces that out. Initially, we start the height profile in some conventional way. With this rule only determines up to a vertical translation, but we start with the height profile going through the origin. And then we let it evolve dynamically. And the dynamics is that when we have a 1, 1, 2 adjacent 1s, and a 0, then this 1 can jump over there, which means that this little valley becomes a mountain. That's how this is the standard convention for exclusion processes. Okay. Now, just a couple of comments. If we have a configuration which has some density rho, then that's translated into an average slope for this height function, which is just 1 minus 2 rho. If you look at a fixed point, the height function is non-decreasing in time. That's clear in this picture. What happens here, we have a change, it goes up. There's no way the height function can go down at any point. And also crucially, if you look at one step of the dynamics, this height function can only increase, as this one did, up to a height if there's already something to its left which is at least that high. So by going up, it cannot go higher than the things which are already to its left. Good. Now let's talk about the low density region. So I'm now going to draw lots of pictures. Here's a typical initial profile, and I want to see what happens to this during the evolution. Here's what happens during the evolution. All right, I'm going to look at some special points, which is the site at which the profile first reaches a certain height. So here they are. Here it reaches height 2, that's P2. Here it reaches height 3, then it goes back down again. Here it reaches height 4, and so on, height 6. So we have this picture with these special points P identified. These don't move in time. I mean, if you look at the height profile later and you apply the same rule, you get the same points. And that's because of what I said before. This point cannot go up. And I'm sorry, what's more important to say is that this won't go up. Not only that, nothing that came before it can reach the same height as this point because it would have needed something at least that high further to its left. So the fact that things can never outstrip what's already to their left guarantees that these sites PK do not change in time. So those points are fixed, but in between them, the height function can grow. Okay, so there it is. This has gone up. You have this is the final configuration, and that's what happens in between these PKs. The profile just goes up. And so what does a final configuration look like? It has these stretches of wiggly stretches, which are just 1, 0 repeated. And then in between there, there's one or more extra zeros. Here there are actually 2 extra zeros. Here there are a lot of extra zeros. So there's some extra zeros in there. Extra zeros, I've just drawn 1 0 here, but I can get several zeros by taking the capital N equal to 0 so that this isn't really there and I get a bunch of zeros. So now we know what happens to any initial configuration. It goes to this kind of final configuration with the N's determined as the difference of these P's that I found. Okay, now let's get the distribution of this A to infinity. This is what it looks like. Now, once we know this PK, go back to here. Once we know the PK, what happens, where the next P is simply determined by what happens after this one that I've already found. That means that this location of this guy is, or the difference rather, is independent of everything that's happened before. The differences are independent random variables because it's Bernoulli. That's where we use the Bernoulli assumption. And that means this sequence of points is a renewal process. So buried in our final distribution is this renewal process formed by these points PK. And another way to spot them, you don't have to go back to the initial configuration. If you look at the PKs, there's always going to be a double 0, 2 zeros right at the point where you reach this PK, because there's a 0 to get there and a 0 just before that as well. So the points of the renewal process correspond to double zeros in the final configuration. Now, what happens between that? That's what you need for the final distribution. So I recall something that you knew all about, but I found out as I was doing this work, the Catalan number. The Catalan number, C sub n, counts the number of these height profiles going from a point 0, 0 to 2n, 0, that is spanning 2n sites, which do not go above the x-axis. So for example, the third Catalan number is 5. That is, you take 6 units apart and look how many profiles wiggle from one to the other, always staying below the axis. And there are 5 of them shown there. And if you go back to C, here you see that's exactly the counting you need to know how many different initial profiles give you the same final profile. So the probability that this thing is some value n is the corresponding Catalan number, which counts these things, and then a factor giving the usual weight for the configuration, which is a factor rho for each down step density and a factor 1 minus rho for each up step, with an extra 1 minus rho because there's a 0 sitting at the end. So that's the complete answer for the low density distribution. So just for amusement, I want to mention a couple of properties of this state, which are, well, not really easy to work out, but we can work out. So let's look at the 2-point function, as a physicist would call it. This is the correlation between the value of the profile at point 0 and at some other point n. And this is expectation. So this is the average of that. And also the truncated one, where you take this and subtract its the product of the two individuals. So this is actually just the expectation, and this is the covariance of those random variables. And there's an identity which we found by accident, which surprised us. That is, this G function satisfies the sum on any two, not any two consecutive things. If you look at an even distance away and the preceding odd distance away, you add these two expectations, you always get the same answer, 2 rho squared, independent of the value of m. That's actually that can be proved in various ways. One way is to calculate the generating function of these GNs. And then, of course, this is just some simple fact about the generating function. And there's a couple of other proofs, but I'm not going to go into them now. Can also ask about fluctuations. I want to think about fluctuations in the number of particles in a box. So NL denotes the number of particles in a box. And I want to look at the variance of that quantity per unit length and take the limit. So that's a quantity which I call V. Now, there's a standard formula for that in terms of the 2-point function, the truncated 2-point function. That is, this V is always rho minus rho squared minus the sum from k equal 1 to infinity of the truncated 2-point function. That's a standard formula which is easy to work out just by writing out this variance, and you get lots of cross terms which can be reorganized into this. But what is this for us? Well, look, every 2 consecutive terms in this add up to 0, because these 2 terms add up to 2 rho squared, and when I truncate, that is, I subtract rho squared from each, I get 0. So if you look at the partial excuse me, the partial sums of this sum, every other one is identically 0, and they go to 0. And so this goes away, and you get simply rho minus rho squared. So the fluctuations of this sort of fluctuations in this measure are the same as for the initial Bernoulli measure. That's the answer for the Bernoulli measure. In fact, that holds in all the density regions. So if I look at this quantity V as a function of rho, I just get rho times 1 minus rho, except at these special points 1/2 and 2/3, because remember, at 1/2 or 2/3, the system was completely rigid. So there were no fluctuations. It was just the measure just lived on configurations of alternating 1s and 0s, or 2 1s and 0s. So there are no fluctuations. So we have this rather strange behavior for this quantity V in the L goes to infinity limit. Now, I want to spend less time on the high and intermediate density range, but I want to make a few comments about it. So let me talk about the high density range first. I said you needed a trick to see what was going on. And remember, I said earlier that once that the final configurations just translate to the right at each, translate to the left at each time step. Now I've forgotten myself which way they go, so I go back, sorry. Okay. They translate to the left at rate 1. So I modify the dynamics to get rid of that. I just add an extra translation by 1 unit to the right at each time step. Okay. Then this limit exists just as it did before, because in this case, the final thing will be frozen. It won't move because I put this extra translation in. And it's very surprising. I'm not going to go through it, but the treatment is almost completely parallel to what happened in the low density region. There are differences, but you have that same sort of graphical analysis, which is almost unchanged. And the limiting configuration in this case looks like this. It has 0, 1, 1 to some power, that's the 2/3 part, separated by 1s, extra 1s. Very similar to what we had before, but now these changes. And again, these n's are independent random variables, and their distribution you can work out by the same way you did before. This is not the Catalan number. This is some other number which involves this binomial coefficient, but it's the same picture as before of counting the number of fragments of height profiles that do certain things. And this identity which we had before, which involved two consecutive values of the two-point function, now just involves three consecutive values. And again, all of this can be proved. The intermediate density range is considerably messier and more complicated, and we do not have a complete answer in that case. So I'm going to just give you a little feeling for that. Again, we modify the dynamics to get rid of this extra translation. So we added translation. Now it's 2 units to the left so that we again have a limiting value. And now the limiting coefficient always looks like this. It's made of a combination of the things we had before, these 0, 1s, which we had at the low density range, and these 0, 1, 1s, which we had at the high density range. They now alternate in some fashion that looks like this. So to give a complete description of the measure, we want to suppose that this eta 0 is distributed by a Bernoulli measure and ask for the joint distribution of these m's and n's. And we don't have it, I'm sorry to say. We do have some information about this. You can find buried in the, not in this, just this eta infinity, but buried in this whole height picture, which I gave you, a hidden Markov process. There is a Markov process there. It basically involves kind of 2 steps from here to here as one state of the Markov process, plus a little bit more information. And if from the hidden Markov process, you can read off the values of the m's and the n's, and in some sense, therefore, get their distribution, but we don't know how to get anything very useful from that. In particular, the identity that we had before, which used to involve either a sum over 2 or 3 things, now involves a very similar sum of 6 consecutive values of the 2-point function equals 6 root squared. But we don't have a proof. We just have this on the basis of simulations. I'm sure it's true, but there's still work to be done to find more information about this intermediate density region. Let me take a minute or two to describe how this map comes out in the intermediate density region. So that before you can worry about the statistics, which we don't know how to do, you have to understand how to go from the initial configuration to the limiting configuration. And that's somewhat similar to what we had before with the picture, but a little more complicated. So here's a quick summary of that. Here's a typical initial profile that has slope. The average slope is 1 minus 2 rho, and that lies between 0 and minus 1/3. So it's overall a downward slope. Now I add some points. Again, now I have 2 kinds of points. I have P's and Q's, which alternate. The P's are easy to define. They're the points which dominate everything ahead of them. So there's nothing ahead of this point, height P, which is as big as P is. That's clear. These P's are the peaks which dominate what's in front of them. The Q's are defined almost similarly, except in this case, they dominate what's in front of them, not in the sense of horizontal lines, level lines, but in the sense of level lines of slope minus 1/3. So if I draw a slope minus 1/3 through this Q, everything ahead of it will lie above that line. And these actually move during the evolution as before. This point up here, a P-type point, moves to the left. This Q-type point moves to the left, but also upward at slope 1/3. So there, the green lines show you how these points move. This Q point moves like that. This P point moves, and they finally stop when they reach the collision point. So this P point that started there will move until it hits the green line coming from the next Q, and then it will stop at that point. Now these P's and Q's still lie on the height profile. So the limiting height profile looks something like this. It follows these green lines, except that, and that's what it looks like. So you can work it out from these. And that's a very symbolic picture. What it really looks like, remember, it was composed of 0, 1s. This is a sequence of 0, 1s. These pieces here, or here it's clearer, this is a sequence of 1, 1, 0s. And so you have that. So we can do that, but getting good statistics, useful statistics of the distribution of these guys, we don't really have. Okay, that's what I have to say about this model. I don't know if there are any questions. I mean, next is.
So you always, sorry, Eugene, you always get deterministic.
I'm sorry, what problem? Say again?
You always get a deterministic configuration.
Yes, I'm sorry. I should have said that at the beginning. This is actually a deterministic evolution. I meant to say that at the beginning. I just forgot to put on the slide. The only randomness is in the initial measure. Thank you. Yes. Now that's no longer true at this stage. Now I'm looking at the partially asymmetric exclusion process where I jump to the right with rate p, left with rate 1 minus p, and these are really rates. Now I'm in continuous time. But again, I have facilitation. This particle can jump because to the left because it has a right-hand neighbor. This particle cannot jump because it has no neighbor to help it. And you don't have to worry about collisions because it's continuous time. So you never have two jumps at the same time. Now, let's just see what happens on an intuitive level. During the evolution, double ones tend to move. Now, they can move in different ways, and this is a very simplified version, but you can prove that the conclusion is correct. You can see this double one here. This one jumps to the right, and you've got a double one move there. That happens again. He's moved there, but now he's next to a double zero. And if this one now decides to jump to the right, you've wiped out both a double zero and a double one, and you're left with 1 0 1 0. And just as in the previous models, you cannot form double zeros or double ones spontaneously. So all that can happen is that the number of double zeros and number of double ones decreases. And therefore, in the stationary state, one or the other of them will have disappeared. Now, this is not very convincing as a proof, but that's the idea, and it's easy to make that into a proof. They can't coexist in a stationary state. That tells you immediately that you have three density regions that are relevant, much as before. While this is a little different from before, you have rho less than 1/2. In this case, all the double ones disappear. So all that's left is double zeros. Well, that's what I called before frozen configurations. Everything is frozen. And any TI state, any translation invariant state on the frozen configurations is, of course, stationary because nothing can happen. So the question of stationary states in this case is trivial. At rho equal to 1/2, the stationary state is it just sits on, again, as it did before, on these alternating configurations of 1s and 0s. At higher density, it's the double holes that have vanished. So you have a situation where you have particles with no adjacent holes. That's the situation at high density. Okay. All right. So now I want to tell you our results. We have some results on both the low and the high density regions. So let me tell you what they are and maybe sketch the proofs briefly, although I don't want to go too long here. All right. So now we already found out what the stationary states are at low density. They're these frozen states. But now I can ask my other question, initial Bernoulli measure, what is the final distribution? Whoops. There it is, sorry. And here's the theorem. The final distribution is independent of P. Surprisingly enough, we were surprised. And it's the same as a distribution that we worked out at low density for the previous model, the F-test. All right. Now I'm going to sketch the proof of that rather quickly, but let me first make a comment. You can look at P equal 1. P equal 1 is just the continuous time version of the previous model. All the jumps take to the right. And every argument that I gave you there involving this height function goes through the same for discrete time as continuous time. So it's the previous argument applies unchanged, and indeed you get the same distribution that you had, the same limiting distribution. So it's trivial for P equal 1. The problem is to show it for others, for other values of P. In fact, I'm not going to use this directly because I'm going to go to do it for general P. I'm going to go to a finite system. So I go to a finite system, but now for P equal 1, I can't quite say it's the same as what we had before because it's a finite system, but the same sort of arguments work. And you easily find that what the limiting distribution is for p equal 1 by similar arguments to before. Now, oddly enough, we don't find this directly for general p. We don't have an argument where for a given p, we know the final configuration, because this is not deterministic. It's got the jumping rates, but rather we directly prove p independence. And the key idea is that adjacent zeros in the final configuration must have been there all the time. There's no way you can form adjacent zeros. I mentioned that before. So effectively, these double zeros in the final configuration separate the evolution into regions which can be considered independent. Here's how that goes. We take any configuration and we can always decompose it into components separated by double zeros. I'll call C of 8 the number of components. Now, here's what I'm going to actually prove. I take a possible final configuration. Possible final configuration means that there are no double ones. Final configurations have no double ones, so they're frozen. And I show that the probability that I achieve that, given that I start with little n components in my initial configuration, is independent of p. I don't show what it is, I just show it's independent of p, and the argument by its induction on the number of components in the initial thing. Now, n equal 1 is trivial. There's only one thing that can happen for n equal 1, and that's this. That is, when you start with one component, you end up with one component, which is this configuration, independent of p. The induction step is, so first, suppose that the final configuration has two components at least. Here's a picture of a final configuration with two components because there's a double zero there and a double zero there. So I can split the system into two pieces. And now, let me not go into detail, but now I can apply my induction assumption on n to analyze what happens over here, to show that what happens over here is p independent and what happens over here is p independent. And there's also independence between these two pieces. So the final result is p independent. Then here I was assuming I had at least two things. The case C of zeta equal 1 is now trivial, and that's the idea of the proof. So the idea of the proof is this induction based on splitting through the double zeros. I'm sorry, that was a quick trip, but it's not too hard to fill in the details, I think. Then yes, I have to go to the infinite volume, which again is not particularly exciting. Now, what about high density? What happens for high density? All right, first of all, I've already argued that every state is going to be supported on the set of configuration which has no adjacent holes. All right, now, I just remind you of a statistical mechanical model called the nearest neighbor hardcore model. Okay, here you have particles interacting on a lattice, but they have a hard core, which says you can't have particles on adjacent sites. That's the only interaction. There's a Gibbs measure for this system. I called it nu bar, rho bar. Rho bar is the density. In finite volume, it just says all configurations are equally likely as long as they satisfy this exclusion, which says particles can't belong in the same thing. Now, if you interchange particles and holes, here you can't have two adjacent particles. If you interchange particles and holes, you get a measure which I call nu rho, which has no two adjacent holes, and that's supported on this set G, and that's the measure we're interested in. So that's just a little background. It's basically saying all configurations which obey this exclusion property of not having adjacent particles or not having adjacent holes are equally likely. And the theorem then is that that is the unique ETIS measure with these at higher density. There's only one, and it's that. I think I'm going to tend to skip things here, but let me just skip the details, but let me give you the basic idea. The basic idea is that we use a coupling with the usual partial asymmetric simple exclusion process without facilitation. That's a well understood process. I think Liggett was the one who understood that. And the main point is that people know all the stationary states for this process, and they're all the Bernoulli states. So once I set up the coupling is just goes, I take a configuration from the ASEP and I get a configuration from the facilitated model, and I couple the dynamics in an appropriate way, I show that there's a one-to-one correspondence between the invariant measures for the F-PASEP, which is what I'm interested in, and for this partially asymmetric process. And once I've done that, I know all the measures for the partially asymmetric process, and then I know all the measures for the facilitated process, and the only one is this measure nu. That's what becomes a Bernoulli measure under this correspondence. Okay. I think I'll omit the details of this coupling. Questions about that? That's all I have to say about that model. So we have those two basic results questions. Of course, trivially, in this case, this measure that we get is independent of P. So here, everything is independent of P. The limiting states are independent of P again, but I think the main point of interest is the uniqueness of this limiting measure. All right.
Gene, a question about that.
Yes.
This coupling, can you use for other things or only in this translation invariant case?
Well, we haven't used it for anything else in this model, but we've used it for we've used things like this in other places, which I'll come back to. So this is the basic idea of this coupling is what I call a substitution map. That is, I take a configuration here in the ASEP and I replace every symbol here by some combination of symbols in the other. So I replace every 1 here by a 1 and every 0 by a 1, 0. So now I get a configuration that looks like this, and there are no nearby zeros. When you do a substitution map like this under certain simple assumptions, you automatically get a correspondence between the translation invariant measures on the two models. And now you have to do something with the dynamics, but we've done it in various cases. We've used this idea to couple the dynamics. And if you can couple the dynamics so that the models stay coupled together as they evolve, then you can get a correspondence. The only thing
the operator transformation with the two dynamics.
Yes, except there's one little. So since you've asked, I'll go to here. Here's the one thing that goes wrong. This is the coupling. I won't talk about that, but the dynamics, suppose it takes a passive configuration to there and an F passive configuration to there. What you just said, if I understood you correctly, was that you would like to have that this A to T is the image of zeta T under the map, and that's not quite true. They can disagree by a translation. And the reason is, essentially the reason is that there's something arbitrary about this substitution map. You have to decide where you're going to start things over here because it's really only the whole translation class. So that comes back to haunt you, that there can be a translation. So you need a little bit of extra work to show that this doesn't affect the fact that they have the same invariant measures, since we're only interested in translation invariant measures. Okay.
Thank you.
Okay. All right, now so now I'm looking at this symmetric exclusion. So I'm back to discrete time. Everybody jumps in discrete time. They jump both ways. They still need a facilitating particle. And now we can have collisions, and under collisions, there's a random choice of who succeeds. So that's where the randomness comes in the evolution. Okay. Now, what we do here is actually study a different model, and I'm just going to give you the new model. It's absolutely equivalent by the same kind of argument that I just discussed with Pablo. So this is an old-fashioned correspondence that people do with zero range processes and so on. You take the configuration of the particle configuration, and you look at a new model where you have what we call stacks, where at every point of the lattice you have an arbitrary number of particles. And the number of particles is just the size of the corresponding block of particles in this model. So here's a block of size 1, you put a stack of size 1 in the stack model. Here's a block of size 0, you put a stack of size 0, and so on. Okay. And here, what is the dynamics? Well, if you go back to this dynamics and think what happens is that if you have a stack of size 1, it can't jump because that corresponds to an isolated particle here. If you have a stack of size 2, that corresponds to this situation, and a particle tries to jump off in each direction. So for any stack of height 2 or greater, 2 particles attempt to jump. And now this kind of collision, there's no, this isn't in the new model. This is just a spacer to keep the track. In this model, what will happen is that if you have a particle size of height 2 next to one of height 3, each will attempt to send a particle to its neighbor, and you'll choose randomly which of them succeeds. That's what the dynamics corresponds here. So you can look at the relationship between these two models as very similar to the relationship, the substitution kind of thing. And again, you can prove that the ETI states of the two models correspond. In this case, there's a relation of what happens with the densities. So the analysis just turns out to be simpler in terms of this model, easier to picture what's going on. Questions about what this model is? Okay. So now there are going to be 3 density regions. Again, low density in the new model, less than 1, that corresponds again to less than 1/2 in the original model. Density equal to 1, which corresponds to density 1/2 in the original model, and density bigger than 1. Now, these are going to be fairly complicated situations, and we've decided that to sort of make it clear what's happening on, we try to organize within each region, we organize the ETI states into what we call lambda families. So a lambda family, as an arbitrary name, it's a set of states together with a natural bijection. So M of X, remember, is the set of all ergodic translation invariant states on 0, 1 to the Z. So this is the simplest kind of situation. And this says that the states in this family of states in the facilitated model can be labeled by the states of this, the simple states on 0s and 1s. Okay. Low density is again uninteresting. In this new model, we still have an idea of frozen configurations. Frozen configurations are those with all stacks less than 1 in height. You can make an ETIS state by taking any ergodic translation invariant state on these things. And that's the answer. And in fact, that's one of these families, because the frozen configurations are just another copy of X. And so you're looking at all the translation invariant states on there. That's exactly what I said was the labeling for this family. So this is a sort of a trivial case where we get this family. Quickly, I should now answer the obvious question, which I answered for the other models. I start with the Bernoulli model. What is the final measure? I can't answer it very well in this case. I have some information, the triple zeros from a renewal process, but we don't really know the answer. However, we do know that the answer we're getting for this model really is different from the answer we got from the previous models. We can see that much. All right, now let's see what happens for rho hat equal to 1. Now there are 2 of these lambda families. Let me talk about the left-hand moving ones. The left-hand moving ones, well, X hat left is a set of configurations that I'm about to describe. I take that set of configurations and I take all translation invariant ergodic measures on those. Those are the extremal states. The set of configurations are configurations which no stack is higher than 2, and 2s and 0s come in always. You have a 2 followed by a 0. That's the only way they can come in. So this is a typical configuration which supports one of these states. Okay. And when you look at that, let me not do it. It's trivial to check out. These configurations simply translate to the left with unit velocity under the dynamics. Remember, this state 2, for example, puts out a particle in each direction. That means this 1 becomes a 2. This 0 gets a 1 from each side, so it becomes a 2. And you track that through, and you'll see that this is just moving to the left. Now, this is again one of these lambda families, and the labeling map comes from the fact that you really have two units here, which are arranged in some arbitrary way. You have two zeros and ones. So if you think of one of these substitution maps where you send 1 and give you 2 0 and 0 gives you a 1, then you come up by the same logic that Pablo was asking about before, by an isomorphism between the states on 1 zeros with the states on this guy. Finally, the right moving ones is obtained similarly. You just reverse the roles of 2s and 0s and they translate to the right. And there are two states which lie in both families. There's the delta function on the state with all 1s and the delta functions living on states where 2s and 0s alternate. Those are belong to both families. All right. Okay. Now, I guess I've got about 5 minutes left, Pablo. Is that right? Or do you want me to quick?
Yeah, you have 5 short minutes.
5 short minutes. All right. So the key fact, let me be very brief here. This paper isn't written yet, isn't finished, but I hope it will be done soon. The key fact is that once you get to this high density region and you get into a steady state, you never have adjacent zeros or zeros, ones and ones and ones. Okay. And you can figure out the dynamics. The dynamics is such now because of this restriction that you always have a particle moving along every bond at every stage of the evolution, to the left or right, which means that you've got a conservation of parity. The parity of the stack at each height is actually conserved. Sometimes it gets 2 particles, sometimes it loses 2 particles, sometimes it gets 1 and loses 1, but you have a conservation of parity. So you've got a huge number of conserved quantities here. We label these by what we call a parity sequence. That's a sequence of zeros and ones, and a parity sector. A parity sector is a set where we know the parity of every stack is simply the parity of this sigma. And those are invariant sets. So we've got this large number of invariant sets. Let me just say that now, given that, you can you want to look for measures on you first find measures on the set where all stack heights are even. And once you have stack heights are even, you can build all ETIS states by using this sigma thing. The basic idea is if everything in eta is even and you add a sigma, which is one of these 0-1 things, you get something with some new set of parities, which you don't. So let me skip over that. Okay, well, here's the answer. I build an arbitrary measure by taking a measure on the even sector, that's this mu hat. I push it into the sigma sector with this map, which adds sigma to everything. And then I take, to get a translation invariant, I take a translation invariant superposition of these guys. Okay. To make that work, I need to know the stationary measures on the even sector, and I'll say briefly that those are labeled by, or there's a Gibbs measure, one Gibbs measure for each one, with a funny 1 particle potential, and we conjecture that this is all, but we don't have a proof of that. Okay. So now I come back to this. This is the formula. Now, if the conjecture is true, then I know all the ETIS states, and they form into these lambda families in a trivial sense, because everything that comes from a measure lambda here with a fixed Gibbs measure on the Gibbs state, as I vary lambda, I get one of these families. So since I'm supposed to finish quickly, I was going to mention, by looking at special cases, you do find examples. I've talked about these measures as extremal. You find examples where the measures are extremal, but not ergodic under space-like translations, because the dynamics interchanges two things. And this is my final slide. This is how all the different families that I've described fit together. This is the density axis. Here we are at low density. Everything here is at density 1. We have the 2 families of left and right measures with their 2 intersection points. And then at high density, we have this whole region. Okay. This region is described by 2 parameters. There's this rho E, which is the density I use in the even sector for my measure. And this parameter, which is, it's really the lambda measure, but to get a one-dimensional thing, I'm thinking of this kappa as the density of the lambda measure. So the measure, let's see, I had it here. The measure, I want to call the measure is measured by the rho hat E, the density, and this parity measure lambda. That's the complete family, or we think it's the complete family of ETIS states at high density, but we still have this conjecture, and that's the end. Thank you very much.
You can unmute if you want to upload. Thank you very much. Is there any question or comment?
Yes, if I can ask a question.
Yes.
Yes, please.
So thank you very much for your talk. It was extremely interesting. My question will revolve mostly on the continuous time model. So you mentioned this mapping with the zero-range process. And so the mapping, I mean, the dynamics on the zero-range process in a continuous time becomes, I mean, at least in a symmetric case, becomes attractive. So my question is, this mapping with the zero-range process, you did not find it useful? It did not help you?
Well, first of all, let me say, maybe I said something. I mentioned the zero range process, but I don't have a zero range process here. If I had started with a simple exclusion process, the usual exclusion process, and done this same kind of mapping, actually that was something else. This was not the thing that was like the exclusion process. So that was actually over here in the symmetric thing. It was discrete time, where what I call a stack model, but people do this same kind of thing to go from a usual exclusion process to the zero range process. But what I'm getting is not a zero range process. The dynamics are just different from the zero range dynamics.
Well, I mean, I don't think so, because we studied with a few collaborators, we studied the symmetric continuous time facilitated exclusion process. And we use very strongly this mapping, and you actually get a zero-range process. It's just that it's a degenerate one where a particle can only jump if it's not alone on its side. But it is actually a zero-range process up to a translation of a marked empty site.
Okay, I'll have to look at that. I have not. It doesn't look like a zero-range process to me, but maybe it is. I mean, for example. Well, particles with height 1 cannot jump. Is that particle? I mean, if you have height 1, you can't jump. If you have bigger height, you jump in each direction. I don't know. Maybe this fits in with the zero range process. It's certainly not the one that I was familiar with, but maybe.
I mean, but it's so I mentioned it because. In the symmetric case, it was extremely useful to have this mapping, mostly for a reason of attractiveness. And I was wondering whether or not it might have been useful on the other asymmetric models.
It may have been. I don't know.
Okay.
Thank you.
Is there any other question? So let me ask a general question about the non-equilibrium case. If you want to do some hydrodynamic to this model, I guess that in the case when you have this map to the partially asymmetric exclusion process, you could export the hydrodynamics from the exclusion to this model and get a different equation probably. What do you think?
I guess so. I mean, you have to be careful. This is, I mean, the map only works when you restrict to this restricted class of configurations, but it may be that in that case you could do something. I don't know. We haven't tried. I mean, this correspondence only doesn't do an arbitrary configuration. It only does configurations where the holes are separated.
In the facilitated, but you can get the configuration in the exclusion and then map it to the facilitated, and for that one you would have the hydrodynamics.
Yeah, possibly.
But anyway, at the beginning you would have one of these equations, but in the limit you will always have this kind of configuration, right?
I'm sorry, I will always have what?
Even if you start with a configuration that is not of this type, that is not mapped from the.
Yes, you will go to this at least in the transition invariant set, and I suppose you will in an arbitrary initial condition.
Okay. Okay. Thank you. Any other question?
All right. Well, thank you again. I will send the slides. I will send the slides without the overlays, just the simple slides. It's probably better.
Okay. Okay. If there are no more questions, let's thank the speaker again. And see the next time. Thank you, Eugene. Many thanks.
Okay. Thank you.